Yes, good morning to all of you. Today in this second lecture, we are going to study the conversion of different networks. Different networks means that is a T network and a pi network, and if these two networks are equivalent to each other, that is the T network and the pi network is equivalent to each other, then we should equate the equations derived in our last class. In our last class, we have derived four equations, that is Z1 OC, that is the open circuit impedance as seen from the 1-1 terminals, Z1 SC, that is the short circuit impedance again as seen from the 1-1 terminals, Z2 OC, that is the open circuit impedance as seen from the 2-2 terminals, and the last term was Z2SC, that is the short circuit impedance as we can see from the 2-2 terminals. Now here in this study, or rather we are going to derive the equations by which we can convert a T network into a pi network or vice versa. So here in this lecture, we actually take use of the three equations as derived in our last class. So the equations which are going to be useful in this lecture, they are Z1 OC, Z1 OC, then Z2 OC, and Z2 SC. Sorry, it is Z1 SC. So here in this derivation, or here in this lecture, we are going to actually use these three equations from the last class, from the last lecture. As you can see that this is the figure A, and in figure A this is the T network, whereas in figure B I have shown a pi network. Here Z1, Z2, Z3 are the impedances, but here ZA, ZB and ZC are the impedances. So taken cue from the last class, that is we are taking use of the equations derived in our earlier class, and for a T network the equations. So I'm going to write here first the T sections, and here the pi section equations. T section and the pi section equations. And for a T section, Z1 OC, it is Z1 plus Z3. For T section Z2 OC, it was Z2 plus Z3. These all equations are derived in our last class. And Z1 SC, it was Z1 plus Z2 Z3 divided by Z2 plus Z3. So these are the equations for a T section. Now I'm going to write the same equations for a pi section, and it was Z1 OC, it was ZA into ZB plus ZC whole divided by ZA plus ZB plus ZC. So this is the Z1 OC equation. Then Z2 OC, Z2 OC was ZC into ZA plus ZB, ZC into ZA plus ZB whole divided by again ZA plus ZB plus ZC, and the last, that is Z1 SC, and it was ZA ZB, ZA ZB divided by ZA plus ZB. So these are the equations for the different sections, that is the T section and pi section. And as you can remember, these all equations were derived by us in our last class. So now we are going to extend our topic, and here as you can see that if these two sections, that is the T section and the pi section, are equivalent, then the external measurements, that is Z1 OC must be equal for both the sections, that is for the T section and the pi section, Z1 OC as well as Z2 OC and Z1 SC should be equal to one another. So if these two networks were placed in boxes and only the terminals were brought out, I have already, in our last class, I have already mentioned about the black box representation of a circuit in which the entire circuit is placed inside a box and only the terminals are came out. So here, when a black box representation is made for a circuit, you cannot recognize what is a T circuit, what is a pi circuit. So in a black box representation, or if the circuits are placed in a black box and only the terminals are brought out, it would then be impossible to distinguish the T from the pi circuit at a given frequency. So equating these measurements, what we can derive. So let's equate these equations. That is, we are going to equate each and every external measurement values. That is, we are going to equate the Z1 OC for the T section as well as the pi section. So equating the T section and the pi section for the Z1 OC, we have Z1 plus Z3 that equals to ZA into ZB plus ZC whole divided by ZA plus ZB plus ZC and represent it as equation 1. So equation 1 is actually, we have derived equation 1 by equating Z1 OC for the T network as well as for the pi network. So I can remove these equations Z1 OC for the T section and the pi section. Now let us equate the terms for Z2 OC and it will give Z2 plus Z3 that equals to ZC into ZA plus ZB whole divided by again ZA plus ZB plus ZC. So here only a simple thing is done, that is we are going to equate the external measurement terms, that is Z1 OC, Z2 OC, and last but not the least, we are going to equate again the Z1 SC and it will give us Z1 plus Z2 Z3 by Z2 plus Z3 that equals to ZA ZB whole divided by ZA plus ZB. So from these we have derived these three equations, equation 1, equation 2, equation 3, and in which we actually just equating the three external measurement terms for the pi network and for a T network. So in our left hand side, these are the parameters we actually derived from the T section or from the T network, and in our right hand side we have the terms for the pi network. Okay, so we have 1, 2, 3, these three equations we have. Now subtracting equation 3 from equation 1. So subtracting equation 3 from equation 1, that is, I'm writing equation 1, the left hand side of equation 1 minus the left hand side of equation 3. Okay, again in the right hand side, that is ZA ZB plus ZC divided by ZA plus ZB plus ZC, and then minus the equation right hand side of equation 3, that is ZA ZB by ZA plus ZB. We Okay, so Z2, Z3 terms can be cancelled, and in the right hand side, let's reduce this further, and it will give us ZA plus ZB into ZA plus ZB plus ZC. Then ZA ZB into ZA, that is ZA square. So ZA square ZB plus ZA ZB square plus ZA square ZC, ZA square ZC plus ZA ZB ZC. I think I have a shortage of the numerator part. So the rest of the terms are written here, minus ZA square ZB minus ZA ZB square. Just follow this, minus ZA ZB ZC. So these are the terms in the for the numerator part, and we can neglect or cancel ZA square ZB with ZA square ZB. ZA ZB square can also be cancelled, and ZA ZB ZC, this can also be cancelled. So in the numerator of the right hand side, we have ZA square ZC divided by the entire ZA plus ZB with ZA plus ZB plus ZC. Have you followed it? Yes or no? Is it okay? Is it okay? So just only mathematical derivations are made. Mathematical juggleries are here. So we have, okay. So let's move on to just I am omitting this equation 3, and then we have with us in the left hand side, we have Z3 square divided by Z2 plus Z3, and in the right hand side we have left with ZA square ZC divided by ZA plus ZB with ZA plus ZB plus ZC. So okay, so let's move on to now. If you look into this equation, or rather the denominator of this equation, left hand side, if you look into the denominator in the left hand side of equation, that is Z2 plus Z3, you can readily consider that we can substitute equation 2. We can substitute equation 2 in the denominator part of this equation. So after substituting the value as we get from equation 2, we are going to substitute this value, that is Z2 plus Z3 from equation 2, and it will give us ZC ZA plus ZB, and in the numerator it will be ZA plus ZB plus ZC, and keeping the right hand side intact, that is ZA square ZC divided by ZA plus ZB into ZA plus ZB plus ZC. So from this, as you can see, that we can neglect or cancel ZA plus ZB from both the denominators, and we have Z3 square. In the numerator we have Z3 square. So we can write here, that is Z3 square will be equals to ZA square into ZC square whole divided by ZA plus ZB plus ZC whole square, or you can derive the value of Z3 from here, and it will be ZA ZC divided by ZA plus ZB plus ZC. So we can derive the value of Z3, that equals to ZA ZB whole divided by ZA plus ZB plus ZC. Is it okay? So from this we can calculate the value of Z3. Now what is Z3? As we consider Z3 is an impedance in the T section of a network, and these right side parameters, that is ZA, ZB, ZC, all three parameters are taken from the pi section. So if you have the values of ZA, ZB and ZC for a pi section, we can readily calculate the value of Z3, which is actually in the T section of a network. So this is the way by which we can convert a pi network into a T network. So if you have given a pi network, you can easily convert it into a T section. Sir, it will be ZC, ZA. Oh yeah. Yes, certainly it is ZC. It will be ZC, exactly. Thank you. It will be ZC. Yes, it is ZC. So Z3 will be equals to ZA ZC whole divided by ZA plus ZB plus ZC. And proceeding in the similar manner. So just by taking ZOZC. No, why ZO? Why ZO? Where from ZO comes? Dipanjan, where from ZO comes? Sir, it will be ZC on the right hand side. Yes, Arindam. But where from ZO comes, I can't get it, Dipanjan. So if you have the three different values, or if you have the entire values of a pi section, we can convert it into the T section impedances, and proceeding in the similar way, we can derive or we can have the values of Z1 and Z2 as well. So just writing the different values of Z1 and Z2, or rather the values of Z1 and Z2, which we can get by going through in this similar pattern. We have the value of Z1, that is equals to ZA ZB. The value of Z1 is ZA ZB by ZA plus ZB plus ZC. It is the value of Z1. You can write it as equation 4. Then Z2, we have the value of Z2 as ZB ZC whole divided by Z1 plus Z2 plus ZA plus ZB plus ZC, and let it be equation 5, and then the value of Z3, that is ZA ZC divided by ZA plus ZB plus ZC, and let it be equation 6. So these are the values, these are the different values, or these are the values of a T network. These are the values of a T section or a T network, which we can derive by using equations 1, 2, and 3, as I have shown here. So these are the three equations by which you can convert, or rather we can convert a pi network into a T network. Okay, so if the impedances of the pi network are known, then we can easily determine the equivalent T network. Is it okay? Is it okay? If you have any questions, Devolina, ZA ZC hobe. Oh yes, it has been corrected. Okay, Dipanjan, I got it. It was ZA ZC. I've read it as ZO ZC. So the confusion here, it is my fault. So I have corrected it, and these are the values Z1, Z2, Z3. So may I proceed further? Only positive values will be taken. No, you are, if in a network theory, in our network theory, these are the magnitudes, or these are the values only given here. So these are not the angles associated with, as we can easily consider that an impedance means it has a positive value, or it has a magnitude, and with it it has an angle. So here only the magnitudes are taken. So these are only the values. These are only the values, and we have to substitute these values here. Okay, Udar. So let's move on to convert the reverse process. Let's move on to the reverse process. That is, we have now, if we have the T section parameters, or T section, or the impedances as given in a T section, and we have to convert it into a pi network. So now the topic, what is I am going to cover is now to convert a T network into a pi network. So now if the T impedances, or the T section impedances are given, how the pi network or the pi section can be derived. So this is the reverse of the topic as I have discussed now. Now to derive those equations, that is the inverse transformation from T to pi. So now we are interested to transform from T to pi, and if we substitute equation 2, if we substitute equation 2 in equation 3, already I have wiped equation 3. So let's rewrite it. It is Z1 plus Z2 Z3 by Z2 plus Z3, and it was ZA ZB divided by ZA plus ZB. So now I'm going to substitute equation 2 into equation 3. Okay, so here you can see that this Z2 plus Z3 must be substituted here. So we have Z1 or we can substitute, which results in, that is, now we are going to substitute, that is ZA plus ZB. If I go on to substitute this value of ZA plus ZB, so it will be ZA plus ZB equals to Z2 plus Z3 into ZA plus ZB plus ZC divided by ZC. So what will we have? Z1 plus Z2 Z3 by Z2 plus Z3, and in the right hand side it will be ZA ZB divided by ZA plus ZB, means that is Z2 plus Z3 into ZA plus ZB plus ZC whole divided by ZC. So ZC will be here. Okay, so now simplifying this, that is Z2 plus Z3, so it will be Z1 Z2 plus Z1 Z3 plus Z2 Z3, and here in the right hand side we have ZA ZB ZC whole divided by Z plus Z3 into ZA plus ZB plus ZC. Now we can cancel this Z2 plus Z3 in the denominator sides, and we have Z1 Z2 plus Z2 Z3 plus Z3 Z1, and that equals to ZA ZB ZC whole divided by ZA plus ZB plus ZC. Okay, now we have also the other three equations, that is equation 4, equation 5, and equation 6. That was the equations for the pi to T conversion, and if we apply the value of Z3. So by use of equations 5, equations 3, equations 4, or rather you can use equations 3, 4, 5 in the right hand side. In the right hand side, that is in the right hand side of this equation, and we can derive the different values. We can find out the different values of ZA, ZB, and ZC. So by equating, by substituting the different values, of Z1, Z2, and Z3, that is from equation 4, equation 5, and equation 6, we can derive, or we can have the values, of ZA, ZB, and ZC in terms of Z1, Z2, and Z3. So the value of ZA will be Z1, Z2 plus Z2, Z3 plus Z3, Z1 whole divided by Z2. Then the value of ZB, it is Z1, Z2 plus Z2, Z3 plus Z3, Z1. You can find it that the entire values of ZA, ZB, and ZC, the numerator remains the same. That is Z1, Z2 plus Z2, Z3 plus Z3, Z1. If you are interested about the detailed calculations, how to find out these values of ZA, ZB, ZC, or Z1, Z2, Z3, you can go on watching my two videos given in this channel, named as pi to T network conversion and T to pi conversion. Or if you type these two, that is pi to T conversion or T to pi conversion, in Google as well as in YouTube, you can find my videos ranked as number 1, number 2. So you can proceed, or you can watch those videos for the complete derivations of these three equations. So the values of ZA, ZB, ZC, as you can see that these equations are also represented by the three impedances Z1, Z2, Z3 in the T section. So here I can conclude as that this is the process by which we can convert a T section into a pi section, or a pi section into a T section. But as you can see that these equations, or the values of these equations, that is, if you consider Z1, Z2, Z3, that is in our last part, you can find out, or rather if you go on to watch these equations ZA, ZB, ZC, to remember this, the values of how to convert Z1, Z2, Z3, or how to get the ZA, ZB, ZC, I think it is important part, that is how to remember these three equations, or rather these 6 equations as a whole. So here a shortcut process, or here this is the process by which you can remember these 3, or rather these 6 equations. Okay, so let's consider this figure. You have to remember just this figure. Follow it carefully. So this is just consider this figure only. and you can easily remember the different equations. Let the impedances are ZA, ZB, ZC. As in the pi section of the figure, we have used in this order ZA, ZB, and ZC. So the order is maintained here, and as well as the impedances for a T section, that is Z1, Z2, and Z3. And here also the order is maintained if you consider the T section of our figure. So these are the six impedances. These are the six impedances, that is the T network and the pi network is drawn in a single figure. In a single figure here, I have drawn the T equations or the T impedances and the pi impedances in a single figure. This is the T section, Z1, Z2, Z3, and this is that is the outermost part is the pi section, that is ZA, ZB, and ZC. So how to remember, how to write these equations? Now this is important. That is, if you consider just consider two different values, two different equations. Let us consider the value of Z1. How to remember or how to get the value of Z1, that is ZA, ZB divided by ZA plus ZB plus ZC. Okay, or the value of Z2, that is ZB, ZC divided by ZA plus ZB plus ZC. So let's consider the three different values of Z1, Z2, Z3 first. How to get these values by this particular figure. Now let's consider, let's see carefully. We have to find out, if we have to find out the value of Z1. So here this is Z1. Okay, so remember one thing, that all the in the denominators of all these three equations, the value is the same, that is ZA plus ZB plus ZC. So here you have no problem, as because the denominators for all the three are the same, that is ZA plus ZB plus ZC. Now what is the value of the numerator part, as the numerator changes in every one of three? So if you have to find out the value of Z1, now here this is Z1, and in the opposite sides of Z1, what are the impedances lies in the opposite sides of Z1? You can find that the opposite impedances are ZA and ZB. So just consider the opposite side impedances for the Z1, Z2, and Z3, and you will get the numerator values. That is, the opposite sides of Z1 here are ZA and ZB. So the numerator is ZA, ZB by ZA plus ZB plus ZC. Let us consider the value of Z2. Now here also you have to find out the impedances lies in the opposite sides of Z2, and you have ZB and ZC. You have ZB and ZC. These two impedances lies in the opposite ends or opposite sides of Z2. So the values of the numerator is ZB, ZC divided by the entire 3, that is ZA plus ZB plus ZC. Again for Z3, this is Z3, and these are the opposite side impedances, that is ZA and ZC. So here you have ZA, ZC in the numerator on the right hand side, and again the denominator is the entire 3 impedances in its sum form, that is ZA plus ZB plus ZC. Have you find it easier? Is it okay? How to find the values of Z1, Z2, and Z3? Is it okay? So just by practicing, you have to remember this part only. That is when you have to find out the value of a t section. Whenever you have to find out the value of a t section by using the pi section, you just consider this figure as a whole, and then you can write these equations only remembering that the denominator part remains the same, and you have to get ready, or you have to get the value of the numerator part, and it is just only you have to put the product of the two impedances, which is actually lies just in the opposite side of the t section here. Okay, so now let's move on how to remember how to find out the values of the pi section. How to find out the values of the pi section, and for this again I am writing the different values of pi sections. ZA, that is Z1 Z2 plus Z2 Z3 plus Z3 Z1, and here the simple part is you can see that the numerator part of these three equations are the same. The numerator parts of these three equations are the same. Uh, so you have to remember only the denominator part of these three equations. So you have to only remember the denominator part of these three equations. So how to find out? So let's check out how to find out the denominators of these three equations. So the numerator part remains the same for all these three, that is for ZA, ZB and ZC, and this is only the product of this is only the sum of the product taking two impedances as a whole. So it is Z1 Z2 plus Z2 Z3 plus Z3 Z1, and now comes the denominator part. Now let's check out where is ZA. Where is ZA? So this is the position of ZA. This is the position of ZA. Okay, and now where is Z2? Z2 is just at the opposite end. Z2 is just at the opposite end of the pi impedance. So in the denominator part, we have to put the value. We have to put the value of the just opposite end T section impedance. So here for ZA, it is Z2. For ZB, where is ZB? So this is ZB, and the opposite impedance is here Z3. So in the denominator, we have Z3. And again for ZC, so this is the position of ZC. And as you can see, the exact opposite side impedance is Z1. So we have to put Z1 here. So I think these mnemonics, or rather this in this shortcut method, you can remember how to write these conversion equations, as because this is mostly important part of this discussion, as because without remembering the values of these conversion equations, without remembering these six equations as a whole, you cannot proceed further, as because if the question, or if it is a theoretical question, that is find out the values or how to convert a T network into a pi, or the vice versa question appears, so you have to derive this entire thing. But if there is a problem, if there comes a problem that is to convert a T network into a pi or a pi into a T, so you have to remember these six equations at once. And this is the procedure, this is the process by which you can readily remember these equations, and you can be able to convert a T network into a pi, or a pi network into a T. Is it okay? Is it okay? Okay, Arindam. So you have to remember just this figure in which the six impedances are in together. That is, we have to draw the T section as well as the pi section. And remember that you have to give the values of the impedances taken in order. So if you mix these values, or if you write these values as you wish, so there will be the problem. Okay, thank you, Kaji Manwarul Islam. So let's move on to our next topic. So we have completed this topic, that is conversion of T to pi or pi to T. So let's move on to our network theorems. I know that these network theorems, or rather most of the network theorems, are known to you, but here in this lecture part, that is these the theorems which I am going to discuss, or the theorems which you have in your syllabus, you have to derive these theorems in just a different way. So let's move on to derive these network theorems. And to start with, so now the topic is network theorems. So now the topic is network theorems, and the first theorem which we have is the superposition theorem. So this superposition theorem is actually a very important theorem. All the theorems are important in circuit theory, but this particular theorem, that is superposition theorem, is very much important as per the application part. Whenever we have a circuit, rather we have a complex circuit in which there are a number of energy sources, there are a number of current sources, there are a number of voltage sources, then the simplified theorems, we cannot apply those. We have to then to find out the value of the current, or to find out the value of the voltage, we have to initially use this particular theorem, that is the superposition theorem. And this theorem states, if you can, you just write it down, as because this theorem is stated in a very different manner, or in a very different way in every books. But the main theorem, but the exact theorem is what I am going to state right now. If you can, just write it down, or if you can't write it down, just mention. I will repeat this theorem once more. Okay, so let's start the theorem. And this theorem, that is the superposition theorem, states that in any linear network, containing bilateral linear impedances, and energy sources. In any linear network containing bilateral linear impedances and energy sources, the current flowing in any element, is the vector sum. The current flowing in any element is the vector sum of the currents that are that are separately caused, to flow, in that element by each energy source, So let's repeat again what the theorem states. The theorem states that in any linear network containing bilateral linear impedances, and energy sources containing bilateral linear impedances and energy sources, the current flowing in any element, is the vector sum. The current flowing in any element is the vector sum of the currents, that are separately caused, to flow in that element, by each energy source. Okay. So to prove this theorem, let's consider this circuit. Here you can readily find this circuit as a T network. So here the two different energy sources are E1 and E2, and the impedances are Z1, Z2, and Z3. We have a current of I1 here and a current of I2 flows here. Okay, so this is the problem. Rather, this is the circuit in which you can find that there are three impedances: one Z1, Z2, Z3, and there are two energy sources. One is E1 and the other one is E2. And here two different currents are flowing in this circuit, that is I1 and I2. So I1 current is generated from the E1 energy source, and I2 will be the current by the E2 energy source. Now let's write the mesh equations, as we know how to write the mesh equations. So writing the mesh equations, if this is our mesh 1 and this is the mesh 2, so write the mesh equations first. That is E1 equals to I1 into Z1 plus Z3, plus I2 Z3. So the mesh equations are E1 equals to I1 into Z1, plus I1 into Z3. So we can take I1 common and we can write I1 into Z1 plus Z3. As you can see, for the impedance Z3, the two currents, that is I1 and I2, are flowing in the same direction. The two currents I1 and I2 are flowing in the same direction for the impedance Z3. So we have to write it as plus I2 Z3 and let it be equation 1. Now writing the second mesh equation, that is for this mesh. So this can be regarded as mesh 1 and mesh 2. Now for the mesh 2, the equation should be I2 equals to, again, I1. We have to write the I1 component first, as because this is the first part, as I1. So again for Z3, the direction of I1 is same. So I1 Z3 plus I2 into Z2 plus Z3. So these are the two mesh equations two mesh equations for this particular network. Okay. Now then, by solving these two equations, we can find out the values of I1 and I2. So the values of I1 and I2, I'm not interested for simplifying these two equations. You are all mature enough to simplify these equations. As you can find that after simplifying these equations, we have the values of I1 and I2 as I1 equals to Z2 plus Z3 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1 into E1 minus Z3 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1 into E2. So let it be equation 3. This is the value of I1. Just you can find this value of I1 by simplifying equations 1 and 2, and the value of I2 you can find it as well, minus of Z3 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1 into E1 plus Z1 plus Z3 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1 into E2. So these are the two values. These are the two values of I1 and I2, and these values are readily, you can generate these values by simplifying these equations 1 and 2. Now let's move on to remove each generators. So now this equation, or rather this figure, so now we are going to apply the superposition theorem, and by applying the superposition theorem we have to find out the values of I1 and I2, how this theorem works. So this is the simplified form, or this is the form which we learned in very preliminary stages of our circuit theory, that is the mesh equations. So now we are going to apply the superposition theorem, and we have to check that whether the superposition theorem gives the exact value, as we can find out from by applying this mesh analysis. So for applying the superposition theorem, as the theorem states that each time you have to remove, or you have to consider the effect of one generator at a time. So here, as we can see that there are two generators, one E1 and the other is E2. So we have to reduce this circuit, or we have to replace one generator at a time, and then we have to go on proceeding. So let's draw the simplified form. Let's draw the simplified form, or if this figure is figure A, so let's draw figure B and figure C. So now in figure B, here I have replaced the energy source. At first I have replaced the energy source E2. At first I have replaced the energy source E2. Remember that whenever a voltage source is replaced, you have to short circuit it. You have to short circuit the voltage source. So here E2 is short circuited. Okay, and we have this figure Z1, Z2, Z3. So this is the energy source E1. E1 is remaining here, and we have to write the current value as I1 dash, and this will be I2 dash. So these are the different values, and this is figure B. We can write, or we can, now we are considering, or we are removing the energy source E1. So now we are removing the energy source E1, and then the figure is figure C, and here these are the Z1, Z2, Z3 impedances. So this is the energy source E2, and let the current be I2 double prime, and this is current I1 double prime. So these are the reduction circuits or reduced circuits of circuit A. Now, from the superposition theorem, from the statement of the superposition theorem, we find out that the sum of the currents of figure B and figure C, the sum of the currents of figure B and figure C equals the current in figure A. Or we can write that I1 equals to I1 prime plus I1 double prime. So the superposition theorem states that these reduced circuits, or whenever we reduce one, or we have to take one energy source or the effect of one energy source at a time, so the reduced currents, or these two currents, that is I1 prime and I1 double prime, must be equal to the value of the current I1 as in the original circuit. Again, the values of I2 prime and I2 double prime, that is the sum of I2 prime and I2 double prime, must be equals to the value of I2. So we can write that I1, so we can write I1 equals to I1 prime plus I1 double prime, as well as I2 equals to I2 prime plus I2 double prime. So from superposition theorem, we can write this. Now, solution of the circuits of B and C. So now if we go on to simplify, or if you go on to reduce figure B and figure C, the values of I1 double prime, I1 prime, I2 double prime, and I2 prime. So we can readily write the values of I1 prime as, so what is the value of I1 prime here? You can find out the values of I1 prime as simple as Z2 plus Z3, as simple as Z2 plus Z3 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1 into E1. So just I'm going to wipe this out and write the values of I1 prime, I1 double prime, and then I2 prime and I2 double prime, and you can find out that I1 double prime, what is the value of I1 double prime? It is minus of Z3 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1 into E2, and I1 prime as Z2 plus Z3, Z2 plus Z3 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1 into E1. This is E2 and this is E1. So solution of the circuits of figure B and figure C. So by solving the figures of B and C, we have the values of I1 double prime, I1 prime, I2 double prime. I2 double prime is Z1 plus Z3 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1 into E2, and I2 prime equals to minus of Z3 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1 into E1. I am writing E1 here. So these are the different values of I1 double prime, I1 prime, I2 double prime, and I2 prime. Now, if we compare term by term with equations 1 and 2, that is, or rather 3 and 4, I think the different values of currents are given in equations 3 and 4, that is the values of I1 and I2, we can find out that the total current proves this theorem. That is, if we go on adding I1 prime with I1 double prime, it will give the values as I have written in the value of I1 in equation 3, as well as if we go on to add it up this I2 prime and I2 double prime, and we have the value as written in equation 4 for I2. So this proves this theorem, that is the superposition theorem as a whole. Is it okay? So before concluding this topic, that is the superposition theorem, I have to mention one thing. Again, to know more about superposition theorem, or rather to know superposition theorem in our mother tongue, that is in Bengali, I have a video in my channel, and it has the entire derivation of superposition theorem. And here I must mention one thing before concluding today's topic, that is here a limitation. Here in the superposition theorem, there is a limitation, that is we cannot go on applying superposition theorem in every corner of network theory. We cannot apply this theorem without knowing the fact that this theorem is only applicable in which the linear network or in which the linear devices are used. As the theorem states that in any linear, that the term linear here incorporates in the statement, as because this theorem is only applicable to the linear network. So if in any circuit in which a non-linear device or a non-linear element is used, we cannot apply this theorem. So in a circuit in which a PN junction diode, in which a semiconductor device is used, we cannot apply the superposition theorem. So this is a drawback. This is a drawback of superposition theorem, as because this theorem is only applicable to a linear network or a network in which only linear elements are used. So today this much, and I am going to conclude this topic on the next day, that is tomorrow. I will present the other two theorems, the reciprocity theorem, and then the Thevenin's theorem, maximum power, Norton's theorem. These all theorems are in your syllabus. That is, but you can find that only network theorems, the term network theorems, are applied here. In what way is this different from KCL or KVL? No, this theorem actually the superposition theorem is states the entire different part. It states that the KCL or KVL, you have to apply one KCL or a KVL. You cannot apply both as well. But this theorem applies to a generator. It may be a current source, it may be a voltage source. Okay, so in a KCL or KVL, we have to take in account that whether it is we have to apply the KCL or we have to apply the voltage law. But here in this superposition theorem, the circuit may contain one voltage source and the other current source, and by calculating this one voltage or a current source, we can actually go on proceeding in a similar manner, and we can find out the resultant current from the voltage source or it may be a current source. So this is the essence, this is the applicability of the superposition theorem. It is quite different from KCL or KVL. Okay, so let's conclude today's topic. Good night all.